We've done a lot of integration techniques so far. We can do U substitution. We've learned that we sometimes can split fractions. Remember, of course, we can only split numerators. We cannot split denominators with addition. We've done polynomial long division when the numerator is of greater order than the denominator. Sometimes that works when they're equal as well. And we've done completing the square. There's also times where we multiply by 1 in order to get the denominator in a form that we can handle. In this case, we multiply the 1 plus cosine x in the denominator by 1 minus cosine x, because then that leads us to a Pythagorean identity. And we learned a very, very important skill, integration by parts. And I use the mnemonic Lipit for that, logarithms, inverse trigs, polynomial, exponents, and then trig functions. One of the most surprising ways we used integration by parts was when we integrated natural log of x dx. Remember, in this case, we let our u equal ln of x, and our dv just equaled dx. Then we learned about trigonometric integrals, specifically powers of sine and cosine, or more generally, cosine to the nth power of x times sine to the nth power of x. When one or both of the m and n were odd, we spun one of the sines or the cosines off and used a u sub with the Pythagorean identity. If they were both even, then we used the half angle formula and then used the first method when one or both were odd. Then we got to trig substitutions. The trig substitutions allowed us to deal with integrands in these three forms: a squared minus x squared, a squared plus x squared, and x squared minus a squared. And finally, we learned partial fraction. And that expanded the types of problems we could solve, that is, fractions in the form of p of x over q of x, where q of x was factorable, there's no common factors between the two, and degree p is less than the degree of q. So are there still more things we can't do? Well, yes. Something like e to the x squared dx, sine of x squared dx, sine of x over x dx. These are all examples of integrals that we can't yet do analytically with the tools that we've learned. Well, what do I mean by analytical? Analytical means exact. So analytical solutions fall into three categories. One, what we've learned so far, that list I just showed you. The next way is using a table of integrals. Those are integrals that other people have found out that we can just refer to. Now keep in mind, on an exam, there's often integration that I'll ask you to do that you could look up on the table that you'll have on the exam. But if I say you may use the table to look up to check your answer but not to find your answer, that means I am expecting you to use one of the methods we've learned before. We could also use a computer using symbolic methods. The one we'll use is MATLAB. That's just one of many different computer methods out there. Sometimes, though, we cannot solve things analytically, and then we need approximate answers, and for that we're going to use numerical methods. This usually involves using a computer, whether using Excel or using a computer modeling system such as MATLAB, to solve these. In this video, we're going to talk about the table of integrals and then the computer symbolic methods. So this is a question that I could ask you to do using a table of integrals. If I look at a table of integrals, one of the listings is this. So in this case, it's obvious that these match, and all we have to do is figure out what our a's and b's are. It looks like a is equal to 2, and b is equal to 9. Not negative 9, because if you notice, the integration that we're trying to match this to already has in the form minus b. So that means this integral is equal to 2 over the square root of 9 tan inverse of the square root of 2x minus 9 all over 9. And hopefully I don't have to warn you, do not do that. I could simplify this to simply 2/3 tan inverse square root of 2x minus 9 over 9. And I can't forget the plus c. Here's a different example. Again, solve using table of integrals. There's not an integral on my table of integrals that has this one exactly. I do see one that looks like this. So what I could do is use my old friend completing the square. See, when your algebra teacher made you learn how to complete the square, little did you know you would be using it again. We take the 6 divided by 2, and I get the 3. Now what I've added to here is 9, which wasn't there before, so I need to subtract that 9. Now I'll need to do a u sub, and I've rewritten 9 as 3 squares so it matches my a that's in the table of integrals. Well, I never told you what this equals, and there it is. So if I go ahead and use that, and now if I go back and put my x back in, if we go ahead and multiply the x plus 3l squared minus 9, then we get back to our x squared plus 6, and this will be our final answer. So now let's talk about using computers to solve things analytically. Again, analytically means exact, so we won't have any decimal approximations. Let's look at sine x times cosine x. We know how to solve this one. The first thing I'm going to do is identify that x is a symbolic variable, and I do so like that. Now I want to find the integral of sine x times cosine x, and I want MATLAB to use x as my variable that I'm integrating over. And I get an answer of sine squared x over 2. If I want this to look a little nicer, I can use the MATLAB command pretty, and ANS, just like on your TI-8384 calculator, means the previous answer. And this is more clear to show that it's sine squared x over 2. Notice MATLAB does not use the notation that we do mathematically when we're writing things out, where it's sine squared parentheses x. This means it's the whole expression sine x all squared. Notice what's missing is the plus c. And there's actually two different answers. We could have also come up with the answer negative 1/2 cosine squared x. Those two work out to be the exact same graph. And if we go to Desmos, our graphing software, we can see that 0.5 sine x all squared is the same thing as negative 0.5 cosine x all squared. You might argue with me saying, well, that doesn't look exactly like the same thing. One's shifted up. But remember, both of these have a plus c on top of each other. So that's how we could easily fix that. So some computer software programs might give you the negative 1/2 cosine squared x. Let's look at another one. The integral of dx over square root of e to the x plus 1. If we use MATLAB to solve this, and you'll notice the square root is sqrt in MATLAB, and e to the something is exp. Get an answer that's a little strange looking. I've written it out here. So that asterisk is multiplication. So we have negative 2. The a tan h stands for the arc hyperbolic tangent. And we usually write that as to the negative 1 power. E to the x plus 1 to the 1/2 power, well, that's just the square root. So that's one answer. But I could have done this manually, and I wouldn't have been shocked to have e to the x's, because I remember the hyperbolic tangent of x was simply e to the x minus e to the negative x divided by e to the x plus e to the negative x. So if I decided to use a u sub for this, I could have u equal e to the x, du equal e to the x dx. Solving for dx would give me du over ex. Of course, I don't want to have a u and an x in the same expression, so I'm going to replace e to the x with u, leaving myself with du over u. So that means our integration is now du over u times the square root of u plus 1. That is in our integration tables, and that gives us this lovely thing. And then if I go back into the x world, I get natural log of e to the x plus 1, square root of that, minus 1, divided by the square root of e to the x plus 1, plus 1, and again, plus c. So we do get answers from our computer methods, but they might not always be in the same form as what we would come up with doing it with pen and paper.